The James Webb Space Telescope has recently observed an astonishing event within our solar system, a significant collision on Neptune. This distant ice giant, once perceived as a placid watcher at the sun's edge, is now revealed to be an active world, prone to sudden and violent disruptions. The impact sent shockwaves through Neptune's atmosphere, creating thermal hotspots that are invisible to human eyes and disturbing its supersonic winds and storm systems. The size of the impacting object was immense, likely resembling a small moon or a large dwarf planet, possibly from the Kuiper belt, a vast area filled with icy, ancient objects beyond Neptune. Thanks to Webb's advanced infrared instruments, this groundbreaking discovery became possible. These instruments can detect faint heat signals and minor atmospheric changes, despite Neptune's vast distance. This capability allows scientists to examine the event with extraordinary precision. The collision released vast amounts of energy, affecting atmospheric dynamics, generating massive storms, and altering chemical structures. Methane, the primary component of Neptune's atmosphere, may have fragmented and recombined into more complex hydrocarbons. Moreover, water or ices from the colliding body might produce exotic compounds under extreme heat and pressure. Essentially, this incident serves as a real-time experiment in planetary physics and chemistry, showcasing how a significant external force interacts with a planet's atmosphere and core. The effects are not limited to the atmosphere of Neptune. The planet's faint ring system and its moons, notably Triton, may have undergone subtle shifts due to gravitational fluctuations caused by the collision. Debris resulting from the impact could integrate into the rings, altering their structure and composition. Additionally, Triton, suspected to be a captured Kuiper belt object, may bear marks from such massive encounters in its history. These interactions give scientists a unique chance to observe how impacts affect the evolution of planetary systems in real time, yielding insights into Neptune and the dynamics of giant planets across the solar system. Neptune's collision also highlights the ongoing activity in the solar system's outer regions. For many years, impacts were viewed as remnants of the early, turbulent solar system. However, this occurrence illustrates that significant collisions can still transpire, reshaping planetary atmospheres and affecting satellite systems. By investigating how Neptune absorbs and disperses the impact's energy, researchers can enhance models of atmospheric shock dynamics, energy transfer, and chemical reactions under extreme conditions. This information will also deepen the understanding of impact physics more generally, with potential applications for planetary defense closer to Earth. Observing the response of a giant planet to such a monumental strike offers a benchmark for predicting the effects of large impacts on Earth and other terrestrial worlds. Moreover, the collision resonates with Neptune's own history. Discovered in 1846 not through direct observation, but by noting its gravitational influence on Uranus, Neptune now reveals its dynamic essence through this sudden upheaval. This creates a poetic symmetry. Initially detected through subtle space perturbations, its atmosphere now bears the marks of a massive disturbance. The event illustrates the vast scales of time and space planetary bodies inhabit. Neptune completes one orbit around the Sun every 165 Earth years, suggesting that significant yet rare events like this punctuate its lengthy planetary existence. From a scientific viewpoint, this incident presents unrivaled opportunities to explore Neptune's inner workings. Shockwaves from the event may have penetrated deep within its atmosphere and mantle, potentially affecting convection currents and thermal emissions. Scientists have long been intrigued by Neptune's ability to radiate more than twice the energy it absorbs from the Sun. This latest influx of energy could provide crucial hints about the mechanisms fueling its internal heat. Each new observation will unveil further layers of the planet, aiding researchers in understanding the functions and evolution of giant planets over time. The implications of this event extend to the study of the outer solar system as a whole. The Kuiper belt, scattered disk, and distant Oort cloud hold countless icy bodies, the majority of which remain undetected. This collision serves as evidence that these areas remain dynamic, with objects occasionally interacting violently with planets. By reconstructing the size, composition, and trajectory of the impactor, scientists gather vital data concerning the population of bodies in the outer solar system and the ongoing processes shaping planetary systems billions of years after their inception. Ultimately, Neptune's collision offers a profound illustration of the forces that continue to mold our solar system. It underscores the resilience of giant planets, the persistent activity in the outer solar system, and the intricate interactions between celestial bodies. This rare cosmic event transforms Neptune from an enigmatic, distant ice giant into a vibrant laboratory for planetary science, chemistry, and astrophysics. It serves as a reminder that even in the farthest reaches of our solar neighborhood, the universe is alive with motion and energy, providing both scientific